Hi, we're going to do chapter 10 this morning, so I'll share my screen. So chapter 10 is on streams and landscapes. When we think streams in geology, we're really talking about rivers for the most part, so this is really a chapter about rivers. Running water is the most important geologic agent in eroding, transporting, and depositing sediment. You may recall in a previous video, I told you the water is going to win. Well, this chapter just goes off in that same direction. The water is going to win. Water is a powerful force in the shaping of the surface of the earth. Let's look at flooding, and in particular the graphic, because it shows you a cross section of a river valley. So you have the mountains off on either side, and then there's some flat areas that you see. Those are stream terraces. I know in the graphic it just calls it a terrace, but we will call it a stream terrace. And then there's this little tiny stream that's running parallel to the larger river. This small parallel stream is called the Yahoo stream. You have a back swamp or a marshy area off to the side over here. We'll see that in some of our maps. You have an oxbow lake. We'll talk about them in a little more detail. I know well, they do have it labeled. They have a point bar deposit right here. There's another one there. You should notice that they alternate, that they're always on the inside of a curve, not the outside, and that the curves in the river, which are called meanders, alternate. So you swing left and then you swing right, and you swing left and then you swing right, and so on. So we have the floodplain, this flat area that the river is cutting into. You'll notice that in this little cut down of the side view, they show you the natural levees, the elevated area on either side of the river. You and I would probably call it the river bank, but in geology, it's a natural levee. And then you have an area labeled alluvium. That is the loose material that a river deposits when it overflows its banks. So if you've got flooding, it's all the silt and debris that the river dumps when you've had a lot of rain, or there's a tremendous push of water from upstream due to maybe melting of ice in the springtime, and it dumps all this little loose fine material, which we call alluvium. Over time, that'll get compressed down and turn into rock in the right set of circumstances. But for us, it's loose material, and almost always it helps a farmer. You'll find a lot of farms that'll pop up on these flat floodplain areas because it's convenient. You have a ready water supply. The area is flat, so it's easy to plow. The soil is loose, and it's usually very rich. You'll also see in our graphic something called an oxbow lake over here. An oxbow lake occurs when a meander experiences a cutoff. So the meander gets closer and closer together at one end until the two sides connect. And then there's a deposit, and the meander actually gets completely isolated from the main river. And when it does that, you're left with this little N-shaped or U-shaped or C-shaped lake, called an oxbow lake because it's thought to resemble the horns on an ox. So on a test, I probably won't give you a picture nearly this pretty. We instead might have this little rough sketch. So on my little rough sketch, I have my hills on either side, and a flat area that's elevated, and a flat area that's low, an elevated area again, and in the very center, this downward part is the river channel. This is where the water would be seen to flow. So if we look at this and compare it to the terms we have, the floodplain is the flat area on either side of the river. So that's what we would find. Doesn't want to go up. There it is. That's what we would find in this location. So we would label that area as the floodplain. So on either side of the river channel, the flat area is the floodplain. Stream terraces are elevated above the floodplain. They are also flat areas. So on our graphic, we find those on either side up above. These are usually indicate a previous level for the river. It can occur in a variety of ways. They can occur because of regional uplift, and that means that tectonic forces just push the ground, maybe the river down and the ground up, and so what used to be wet is now dry. It can be a result of a change in climate. Maybe it used to rain a lot and now it doesn't, so the water level drops. Or it could be a drop in what we call base level. Base level is where the water finally ends up. It could be the ocean, it could be a large lake, it could be an underground lake where the water hits a resistant rock formation. So there are a variety of ways you can have a stream terrace. And then the last thing in our graphic, and we'll reveal it, is the natural levee, that elevated area on either side of the stream channel. So if I gave you this drawing, you ought to be able to pick out these different places on it and identify them for me. So this version of the graphic as opposed to the prettier one with all the colors. Here's some more features. This one in particular shows you the stream terrace and points out it's a remnant of a former floodplain. So it's a former level for the river. So you can see the river's cutting through, and here's the new floodplain, and the terrace represents a previous one. Here is a photograph. So in this photograph, the river is right here. The river is right there. And this area is a stream terrace. It's the former floodplain. And we've already said that the natural levee is the increase in the river's banks due to the deposition of material during floods. So it's just the banks of the river, the natural levee. So how does a stream transport sediment? Well, the agitation and the velocity of the water carry the load along. The material that a river transports is called its load. We've got a nice little graphic to help show us what happens. So some of the material, usually the heavier material, gets kind of bounced along the base of the river's channel. Some of it will do a sort of bouncy motion. It comes up and down and sort of hopscotches along. Some of it does more of a grinding motion as it skitters along. Some of it is suspended. If it's small enough and light enough, it'll be suspended up in the water itself, and some of it is actually dissolved in the water. When a river passes over rocks and soil, if there are any salts in the rocks and soil, they get dissolved by the water, and then that's carried along with it. So that's the dissolved load. It's the material is actually dissolved in the water. The suspended load is just a little small material that is too lightweight and it won't settle out, and the water, as long as the water is moving and agitated, the suspended load is going to stay suspended. Normally the suspended load is what gives the river its color. So the Catawba River here in Hickory always looks a little orange because the suspended load is mostly little bits of clay from the soil, and they're teeny tiny and have an electric charge on them that keeps them suspended. When it rains, it looks even more orange. There are places where rivers and lakes don't look that color. If you live in an area that has a lot of glacial activity, then the water tends to look a really pretty milky blue. It is just gorgeous. If you live someplace where the water is very clear, it's going to look a very sky blue color. Moving right along, let's look at some of our parts to it. So the bed load, as I said, is one of the 3 parts to the load. It takes up about 25% of the total load, and that's the big, heavy stuff. And again, the material bumps and jumps along the stream channel itself. The bed load is sorted by size. So what that means is that the heavy stuff gets deposited pretty close to where it entered the water, and it's always on the bottom. The lighter material will travel farther downstream, and it will eventually then settle out on top of heavier material. The material in the river is also broken down or worn down by abrasion. And we've talked about this before. River rocks tend to be more rounded, they're softer in appearance, they don't have sharp edges on them. The longer a rock is in the water, the more well-rounded it's going to be. Normally, bed load only moves if you've got seasonal floods that give you really high, fast-moving water. Normal times, the bed load just stays where it is. The suspended load is the part that we said stays in the water because the water is agitated. It is moving downhill and fast. And so it's this natural turbulence that keeps the water stirred up and makes the suspended load part of the river's movement. And I also mentioned that the particles in the suspended load have an electric charge. They are ionic in nature. And so what that means is you might have all those clay particles I talked about in the Catawba River. Those clay particles have a positive charge on them. And in physics, we know that like charges repel each other. So 2 positive charges are going to push away. So that means those clay particles are not going to clump together. They're going to be forced away from each other. So they're going to stay too tiny and lightweight to settle down because of weight. And the turbulence of water is going to keep them agitated. So as the suspended load is carried along, it usually gives, again, your river its muddy appearance or its color associated with it. It's the color. Not all rivers are muddy. Ours just happens to be very muddy. I mentioned the electric charge on it. Now, as a river approaches the ocean, the electric charge actually changes because of the salt ions. So salt ions are positive and negatively charged, and they will attract an oppositely charged part of the suspended load. So those positive clay particles are going to be attracted to negative ions in the water. The more salty the water, the more negative ions you'll find. And so the clay will clump together, or anything in the suspended load will clump, and then the weight of it's going to let it settle out. That means that even though the river is muddy, the ocean is not. So the salt in the ocean gets into the mouth of the river right before it enters the ocean itself, and helps the material to clump and settle. And also gives rivers their wonderful deltas. The Nile Delta was full of great natural resources because of seasonal flooding that brought topsoil from upstream downstream and allowed farmers to have to plant crops. We've talked about the salt in the ocean. So where does it come from? An ocean gets its salt from river water. Well, where does the river water get its salt? Well, it gets its salt as the water moves over every rock and little bit of soil in its travels from where it starts out, usually high in the mountains, until that river water ends up in the ocean. So as it passes over, the water will actually dissolve chemicals that are water soluble. And so bit by bit, it carries it along to the ocean. Now, when the water in the ocean evaporates to make clouds and rain, the salt stays behind. And what that means is that the older the ocean, the more salty it will be. So when we can tell something about the age of an ocean based on its salt content. If an ocean doesn't have very much salt in it at all, it's not considered to be very old. The older the body of water, the saltier it's going to be. So let's talk a little about that dissolved load. The dissolved load only makes up about 10% of the total load, and I've told you that that material is held in solution because of a chemical reaction. The water in the river actually dissolves chemicals from the soil and the rocks that the river water washes over. Let's talk about some drainage patterns. We have 4 we will mention today. So the first one is the dendritic drainage pattern. It is described as looking like a tree branch. The one to the right of that is the rectangular drainage pattern, and it has branches that make sharp turns. The one on the lower left-hand side of our graphic is the radial drainage pattern, and you have water moving outward from some central high elevated area, and most people describe this as looking like spokes on a wheel. And then the very last one is on the right hand side, on the bottom right corner, is the trellis pattern, and that is where the water runs in little parallel channels because of resistant rock separating them. So let's look at some of those details. We've got that one big graphic. We'll look at them individually. So the dendritic pattern is associated with homogeneous structures. That means that the surface is all pretty much the same. There's no single preferred direction for the water to flow in. And so your stream looks like a tree branch. I would expect you not only to know the definition of the dendritic pattern and what kind of surface it travels over, but to be able to draw one for me. So it looks like a tree branch. The rectangular drainage pattern, I've already said the turns that it makes are 90-degree angles. And this is because the rectangular drainage pattern happens along fault zones. So the rock cracks and breaks, and it makes these sharp angles in the process. And the water then follows along these cracks. Our third one is the trellis pattern. Our third one is the trellis pattern. And as I've said, it's the one where you have parallel channels for the river, and that's because separating those channels is resistant rock. So you have an area of resistant rock and then less resistant rock and then less resistant rock. So in this diagram, the shaded is the resistant rock, and the area where the water is moving through is the less resistant. And the end result will be that your stream has multiple channels and they run parallel to each other. And our last diagram is the radial drainage pattern. On the radial drainage pattern, the water moves out from the center of a high elevated area. So it rains on the mountain and then rolls off. I've always thought it looked like a bloodshot eye, but a lot of places describe it as looking like a wagon wheel. Now, something we haven't defined, but we will in lab, is a braided stream. So a braided stream is a stream that separates and comes back and rejoins itself. You see these in areas where there's a lot of glacial activity because the glaciers bring in loose sediments. So there's not a lot of water then when the ice melts. And so you have usually a flat area with a lot of loose sediment, and the water sort of just branches out around any elevated rocks, but then comes back together. So braided streams have a lot of little islands in the middle of them because the water separates and then rejoins itself. So here's an aerial view. The second photograph is more of a ground level view, and you can see these little low islands in the river channel. And again, you tend to see this in flat areas. As I've said before, places usually where a glacier has passed over. Not always, but usually. We did mention Oxbow Lakes. Here is an overhead photograph of a river that shows not only that it's a braided stream, here you can see the little islands, where the channel splits and separates and then comes back. But here you can see the isolated C shape of the Oxbow Lake. Here's another one over there. So the curves in the river, the meanders, this one used to come all the way out and then swing back and out. And this one used to come all the way over here and then swing back. And as you can see, over time, it's gotten isolated from the main body. So it's been, a meander is cut off from the main stream and then becomes an oxbow lake. Here's another overhead photograph, again, the main river. And here's the Oxbow Lake to the side. And here's a series of diagrams sort of crudely showing you how your meander gets cut off. They don't have it coming together nearly as much as it really does. And then the isolation resulting in an Oxbow Lake. I think that's it. So we will stop the chapter and the record.